Yeah, thank you very much, Eli. We are very pleased and honored to have as our last speaker, Mr. Laרי Jaimes, who has a very long and distinguished career in the U.S. Air Force for many, many years, which he retired as a Lieutenant General. Part of his duties in the Air Force, I'm not going to list them, include some relation to space, and then after retirement, Lieutenant General Laרי Jaimes became the Deputy Director of JPL, Jet Propulsion Laboratory. For the astronomers among us, when you hear the name JPL, you always know that it's related not to one and not to two, but to several very, very important astronomical missions. And Mr. Jaimes is going to tell us more generally about the policy of NASA in the near future regarding space astronomy. Mr. Jaimes, please.
Well, good afternoon. It's certainly an honor to be here and give you a perspective on what we're thinking about at JPL, especially with respect to planetary exploration and Earth exploration. You certainly heard Eli talk about the partnership that we have here in Israel, and that's a very important partnership to us, and that's certainly a very important program as we move forward in terms of really taking advantage of what LIGO has given us from a gravitational wave perspective. But I do want to give you a broader perspective, certainly as we look out to what we have currently accomplished. And again, the first talk was great, talking about what we've done at Juno and Saturn, but also just talk about some of those other missions that we're currently flying, as well as some of the missions that we will be executing in the future. But we all have to start somewhere. This is what we call the Suicide Squad back in 1936, trying to determine how to build rockets, Caltech students and professors. And this is really the genesis of JPL. We also launched America's first satellite, the Explorer 1, and I bring this up because tomorrow is the 60th anniversary of the launch of Explorer 1. So we'll be celebrating that back at JPL and Caltech in a big way tomorrow. A very iconic picture there that you see with Dr. Pickering, who was the head of JPL, Dr. Van Allen, for which the Van Allen belts are named, and Explorer 1 discovered the Van Allen belts, and Dr. Wernher von Braun, who helped us build the rocket that got us up into orbit. So a great day tomorrow to celebrate that. JPL has a history of firsts. The first soft landing on the moon was Surveyor 1, the first landing on another planet with Viking, Voyager 1, which I'll talk about in the next slide, and then we've been on Mars operating since 1997 and doing some incredible science. And really for JPL and for NASA, it's all about the science, understanding what the science questions are and developing systems that will help us answer those hard science questions. We currently fly 17 spacecraft around the solar system and around the Earth, everything from Voyager, which is outside of the solar system, many Earth science missions which look down at Earth like Jason 2 and CloudSat and NEOWISE looking out for near-Earth objects. I'm not going to go through all of these, but they range from those planetary explorers to those Earth explorers to looking out beyond the universe or beyond the solar system with spacecraft like Spitzer, our ultraviolet spacecraft, and Dawn flying around the asteroid belt. So Voyager 1, it is indeed humanity's first interstellar spacecraft. And the science we have gathered from this have certainly been amazing, especially as we've really understood the end of the heliosphere and what that entails in defining that, the end of the solar system, if you will, and now measuring that intergalactic medium, that interstellar medium that allows us to really start to understand how the plasma waves are coming in, galactic particles, and those sorts of things. And the amazing thing is we celebrated 40 years of operation of Voyager last fall. It was launched in 1977. And the fact that it's still operating today, I think, is a testament to the engineers that designed and developed that system back in the mid-70s. And most of the instruments are still operating. Really, the life limiter for us on Voyager will be the nuclear power source. Over time, the plutonium gradually decays and we start to lose power. So probably in the early 20s, we'll have to start turning many of the instruments off just to keep the overall system operating. But still an incredible mission. You saw some of these highlights from Saturn. This is from our Cassini spacecraft. Again, before we sent these spacecraft to these outer planets of Saturn and Jupiter, as was stated earlier, we really didn't understand that there was water that existed outside of the Earth zone. So the fact that we have these icy worlds, these water moons that were highlighted in the JUICE presentation is an incredible scientific discovery in the last 10 or 15 years. And you saw this picture in the JUICE presentation. These are those geysers that are coming up from the moon Enceladus. The incredible thing was that we took that Cassini spacecraft and flew it 30 miles above the surface of Enceladus right through these geysers and collected samples. So we were able to understand the composition of the water that's down buried beneath that icy surface. You also heard a lot about Juno. Juno went into orbit around Jupiter on July 4th, 2016. And I won't talk about a lot of the science because you heard that in the JUICE presentation, but really its mission is to understand what's going on below the clouds of Jupiter. And again, he highlighted many of the findings over this past year that have really opened our eyes to that interior of the planet. And of course that's important because it really helps us understand what was our initial solar system made of, because Jupiter, we believe, was the first planet that formed, and therefore if we can understand the composition and ideally start to peel back its history, that will give us a lot of insight into our early solar system. This is a similar picture from what was seen earlier with the flyby, but it just gives you a great picture, especially as we come over the poles, something that was totally different and really unknown before Juno actually flew over the poles and took these images. And of course, we flew very close to the Great Red Spot, and trying to understand what energizes that, what keeps it going, is all a part of the Juno mission. As I mentioned briefly before, Dawn has been an incredible mission for us. This is an electric propulsion spacecraft that's examining the asteroid belt. So its mission was to fly to the two largest asteroids, Vesta and Ceres, using electric propulsion. So it's really been monumental in two respects. One is the fact that we have an electric propulsion system that's operating in the outer solar system. It's been running almost continuously for years and is still operating. We first flew around the asteroid Vesta, which is the second largest asteroid in the asteroid belt, and then we are currently flying around the asteroid Ceres. And Ceres and Vesta both are really not what I would call your typical asteroids. They're really what the astronomers call protoplanets. So they're really small planetoids. Ceres is very interesting because just like some of these other outer moons, this asteroid has ice on it. It even has cryovolcanoes where the ice is pushed up from beneath the surface and kind of ejected from the surface. So it's a very interesting asteroid or protoplanet that we're finding out a lot about, again, the early solar system, and probably worthy of future exploration. As I said, we have operated on Mars continuously for over a decade. We show the picture of our two rovers here. Opportunity on the left, our smaller rover, is now operating on the surface for 14 years. It was thought that we would operate for about 90 days on the surface of Mars. So an incredible mission. It still continues to do incredible science, and we operate that system day in and day out. And of course, our flagship rover is the Mars Science Laboratory, MSL, or Curiosity. Just to give you kind of a sense of where we are today, this is the base of what we call Mount Sharp. We landed in Gale Crater. Gale Crater is it's kind of a flat area in the exterior part of the crater, but in the middle is this large mountain called Mount Sharp. So we landed in Gale Crater, a nice flat area that we could land safely in. And since our landing about 5.5 years ago, we've been continued to explore that flat area, and now we're making our way up Mount Sharp. And so you can see these various layering strata here, and that's really what the scientists are interested in now, is to make our way up the mountain. And the reality is we're getting close to this area right now where we can start to examine the difference between this area and this darker area, and really look at the geological history of Mars, because each of those strata represent a different geological age for the Martian planet. But you can also see that driving on another planet is not easy. This is pretty tough stuff to drive around in. And in fact, we found that our aluminum wheels have been damaged. They have holes in them. So we kind of have to drive very carefully when you go over terrain like this on a daily basis. But as I said, our focus is always the science. And of course, the big question about Mars is, could Mars ever have been habitable? And the answer to that is yes. With our exploration in Yellowknife Bay, which is near the area that we landed Curiosity, we've shown that water was present there in the past. It was present in large quantities, and it was the type of water that could sustain life. Now, we have not found evidence of life either in the past or today, but we have shown that the conditions existed that could indeed support and sustain life. So really the big questions we try to answer at JPL as we look to the future. First, how did our solar system form? You see that in the Juno mission. You see that in other missions. Is there life elsewhere in the solar system? Certainly with our Mars missions, with future missions to Europa. Those are the questions we want to answer. Does life currently exist in some form, or could it have existed in the past? And then, are there Earth planets like outside of our solar system? Exoplanets, that is certainly a big area of investigation for us today. With Kepler, we have found a multitude of exoplanets. I think we're now up to 26 in the Earth zone, or the habitable zone that we found around other stars. Over 3,500 confirmed planets around other stars. So with Kepler, we've really shown that probably every star system has a planet or multiple planets around it. And again, 25 or 30 years ago, we did not even know if there were any planets outside of those in our solar system. And then the third area we focus in is really looking back at Earth, understanding our planet. And in the United States, the Earth Science Decadal Survey just came out and really validated these particular areas that we focus in at JPL. One is really understanding the water cycle, what's going on with sea level, what's going on with water availability. A second area we focus on is the carbon cycle, carbon dioxide, its creation, its absorption, and then finally understanding extreme events. How does the Earth deform? How does gravity change over time with the change in water and salinity and those sorts of things? So those are areas that we focus on at JPL, and as we look to the future, here are some of the things that we're doing to start to continue to answer those questions. This is InSight, which is our next mission to Mars. We talked about exploring the interior of Jupiter. InSight will help us explore the interior of Mars. So this is a partnership, a very great partnership between JPL, CNES, the French Space Agency, and DLR, the German Space Agency. So this is a lander, not a rover. It's going to launch in May of this year, so about 5 months from now. And once it lands, we will deploy two systems. One are very accurate seismometers that you see here, really covered in a covering to protect them from any wind impact. These seismometers will measure Mars quakes, they'll measure bombardment of the surface of the planet, and with that information, as it propagates through the planet, we can start to understand the core of the planet. And then we will also deploy this device that will penetrate beneath the surface, probably down to about 6 meters, and when you're at that level, you can start to understand the core temperature of Mars, and so we'll be able to put together a very explicit picture of what the core of Mars is like. We're also building our next Mars rover. It will launch in 2020, and it also may have a companion, a helicopter. So Mars 2020, its key focus is it has much more sensitive instruments than the current rover on the planet, which will allow us to look even more extensively for signs of life or signs of past life. But it will also take samples that we'll store on the surface of the planet for an eventual pickup and return in the mid-20s to Earth. So it's really the first component of a Mars sample return. The helicopter is a technological demonstration. We're briefing that to NASA actually in the next couple of weeks to see if they will fund that to go forward or not. So we'll see if that gets funded. But we've proven that we can fly a helicopter in the Mars atmosphere in our vacuum chambers. The Mars atmosphere is about 1% of the Earth atmosphere, and we've actually built this and demonstrated and flown it in the thermal vac chamber at JPL. You've heard a lot of talk about the icy moons. Our next major mission to the outer planets is going to Europa. You can see this very close-up view of the surface, very fractured, ice and so on. But our intent is to, in 2023, launch the Europa Clipper. That will go in orbit around Jupiter and then pass by Europa periodically every 14 days or so, and allow us to really start to do reconnaissance and science on that moon. Ice-penetrating radar so we can understand the thickness of the ice, magnetometers so we can understand the magnetic field, but really do a lot of reconnaissance for the next mission after that, which is the Europa lander. So we are designing that right now for a launch probably in 2026 or 2027. So once we have the Europa orbiter in place, that will give us the reconnaissance we need to ultimately develop the information to go land on the surface and do science on the surface of Europa. One quick point we talked about in the first discussion about going to the outer planets. We intend to launch the Europa Clipper, the orbiter, on the Space Launch System, which is the new NASA rocket, the very large rocket. And because of that, we can go direct to Jupiter. So instead of 7 to 8 years to get there, we can get to Jupiter in less than 3 years. So that really changes the whole dynamic of outer planetary exploration, and we're very excited about that. Going back to the asteroid belt, this is a mission that will go to the 4th largest asteroid called Psyche. This is an all-metal asteroid, and the reason it's very interesting for the scientists is scientists believe it is the core of a protoplanet where the surface has been stripped away by asteroidal bombardment, and we can examine that core, that planetary core, directly with our spacecraft. So we're building and designing that spacecraft now, and that will launch in 2023. And then as we look back to planet Earth, this is the NASA ISRO Synthetic Aperture Radar Program. This is our partnership with India, the Indian Space Research Organization. This is a joint L-band, S-band synthetic aperture radar, which will allow us to do things like biomass measurement, coastal deformation, glacial change measurement. So the first time we've ever integrated an L-band and S-band on one SAR payload. So we're excited about that. We also have another joint program with CNES. This is called Surface Water Ocean Topography. This is a radar interferometer satellite, so 2 radars on those booms. We do interferometry. This allows us to do a lot of measurement of water bodies, so we can very accurately measure ocean height, which we already do, but this will also give us a lot of information on the currents and the eddies in the ocean, as well as allow us to measure fresh water bodies, which we have not been able to do in the past with our current radars in orbit. So that's on schedule to launch in 2021, and as I said, a joint program with the French Space Agency. And then our next Earth Science launch is coming up in April of this year. Measuring gravity is very important. We heard in the Grace the first presentation on JUICE about how they would measure the changes in gravity for the moons of Jupiter. This measures differences in gravity on Earth. And we can actually tell if aquifers have been depleted by the lack of water and those sorts of things. This is a follow-on to the first GRACE mission, which ended back in the fall of this past year, 2017. So these missions, these satellites are currently at Vandenberg Air Force Base, being prepared to launch in April, and will produce exquisite gravity measurements for the Earth. And I think I've touched on most of these in terms of upcoming launches, but we have a host of spacecraft between 2018 and 2022 that are all in some form or process. We also do CubeSats, things like RainCube, which is the first time we've ever built a Ka-band radar and put it on a 6U CubeSat. And then we also send missions to the space station like the Orbiting Carbon Observatory 3. So looking back at the Earth, looking to the outer planets, and looking beyond the solar system, all a part of the mission at JPL. So thank you for your attention, and thank you for that quick walkthrough.